Hello. Oh, okay. I think our recording started. So let's just start our new topics here. Um, Before the test, we went through the calculation of line integral for a vector field. If you guys remember, the line recall the line integral for vector field f over the path C in three-dimensional space or two-dimensional space is written in this way. And here C is given by this path, this vector valued function C of t. Well, depending on its dimension, we have C of t to be two-dimensional vector. Okay, obviously, yeah, this is C is giving for the parameter between two constants A and B. So this is our notation. Okay, we can also write this as if. So here I think we should mark the second point. So this vector field F could be written as F sub 1 and F sub 2 in 2D. Well, in 3D, it'll be having three components for sure, right? If we write this in 2D, so in 2D, the line integral of vector field will be written as f1 dx plus f2 dy, and then the integration is on the path C. So those are the notation we stick with. All right, and one thing we want to point out is that this both f1 here are indeed x and y function in 2D, but in 3D they could be a function of three independent variables for x, y, z. All right, so those are the review of notation involving the line integral for vector field, especially for this two-dimensional vector field. And here, we also want to review a little bit the so-called the conservative vector field, and the line integral for conservative vector field does not really depend on the path. It's just depending on the starting and the stop, the point of your path. So that is another thing we want to review. But here, maybe we shouldn't talk too much about it because our new topic is about this, the Green theorem. So what is the context of the Green theorem? Okay, so here we want to point out for 2D calculation, we have the Green theorem. For F, the vector field is having two components, F1 and F2. Both of them are function of x and y variable. And for this vector field, and we want to say over the domain D, and here we should say this is a simply connected domain. Okay, so there's no hole of a single point inside of the domain over the domain D in xy plane. And we also want to point out the edge of the domain D is denoted by this partial. D. Okay. Then the double integral over the domain D can be linked to line integral along the edge of the domain D, which is partial D in the green theorem. Okay, so essentially the green theorem is making connections between the double integral and the line integral. And let me formulate it in this way. Remember, this green theorem is involved with the vector field F. So okay, so here is what we have. So the double integral over the domain D for this particular integrand, which is related to the vector field F. Okay, and then the Green theorem is establishing the connections of this new line integral F along the edge of the domain with this particular double integral. Okay, so remember for this line integral, we could also write this as f1 dx plus f2 dy, and here this f1 and f2 are just the f2 and f1 in the left-hand side of this green theorem. Okay, and the illustration is like this. If you have this domain, for example, simply connected, so there's no hole. This is D, and the edge is a partial D. And here we also want to make the claim. Here, this partial D, which is the edge of the domain D, it has to have a positive orientation. So what does that mean? That means at any arbitrary point along the domain D, for example here, you can either go counterclockwise or clockwise. The positive orientation is the counterclockwise direction. Orientation. So if you are a little, if you imagine you are standing on the edge of this domain D, when you are walking around this domain, your left hand is always always on the inside of this domain. So that is the positive orientation. Okay, so now we are connecting the double integral with the line integral for this vector field. And this is a very important, very useful theorem for us to use. And here now, we already stated the theorem. This is the theorem. So it is connecting the double integral and the line integral. And we want to sort of, we don't want to prove this because it takes some effort and theory. But we could verify this, right? So let's verify. Green theorem for vector field capital F, which is given by little x times little y and y over the domain given below, which is this one. So this is x, this is y. Okay, so this is our domain D. All right, so obviously this domain D has the edge, which is a part of a circle. Well, this is the whole circle, but for this domain, the edge has two pieces. The part one of the domain D is this one, indeed, and this part two is having the equation to determine the the bottom or base of this domain is the y equals 0 equation. Okay, so we have two very important pieces, because if you only have one piece, you are not going to form this domain. This domain is a half circle, right? Or half disk. Okay, according to this given question and the Green theorem, what do we know? What we can comment on? Well, for this vector field, I have this to be f1, this to be f2. So what we better to write is f1, capital F1 is x times y, capital F2 is little y. So this is our vector field. And according to the Green theorem, due to Green theorem, we have a double integral over the domain D. And here, remember, it's partial F2, partial x minus partial F1, partial y. So how do you remember this partial derivative and F1, F2? Remember, here the derivative is always start with the derivative with respect to x. And here, the F1 and F2 are the component of vector field for corresponding to the y and x direction. So this is the f on the y direction, but take derivative with respect to x and subtract the other cross. So this is the left-hand side of this Green theorem, and this is supposed to be equal to the line integral of this vector field f with respect along this edge, right? So in terms as we said, this has to be f1 dx plus f2 dy. Okay, so let's say establish to verify. So then we want to comment to verify the Green theorem. What do we need to do? We need to compute the left hand side and right hand side of the theorem to check if they agree with each other. So this is our plan. So obviously we have to identify what is the left-hand side. Well, the left-hand side is here, and the right-hand side, well, this part, the line integral is the right-hand side. Okay, so let's just compute the left-hand side first. Left-hand side, we have a double integral, partial f2 partial x, and as we said, f2 is this, just the y, minus partial f1, which is x times y. Take the derivative with respect to y, and then dA. Okay, so this is what we have. Well, there's one thing we didn't prepare well yet, which is how do we describe this domain D? The domain D, maybe we can do it here, is the half disk, right? Obviously, if we write this in the xy coordinates, obviously, x is bounded between -1 and +1, and the y, if we treat this as a type 1 region, the y will be bounded between 0 and the curve, the half circle on top, depending on where your x is, right? So the top boundary for y will be 1 minus x squared. So this is our domain D. Okay, and now on the left-hand side, we can keep computing by treat this as type 1 region after we get this here, right? So we fix x as the variable for the exterior integral from -1 to +1, and then for y, we're integrating from 0 to square root 1 minus x squared. And the integrand over here is very easy to compute because, well, maybe we should do this. What is partial y partial x? It's supposed to be 0. And partial x times y partial y is x itself, right? So now we connect here. So the integrand is just a negative x, I think. Okay, so we have the iterated integral set it up, all right, which is, well, this negative x, we are integrating it with respect to y, so it is just negative x times y. And the y is between 0. So this is what we have. Okay, so this is what this is. We got to plug in negative x times y. Well, here y is 1 minus x squared, and then minus, well, we can multiply this. We can take this factor negative x out, which we keep here, because when we work on the y evaluation, x is supposed to be just a constant. So, okay, so this is what we have. All right. So, well, because this term is 0, then that is always 0. So now we have -1 to 1. So this is, we have taken this negative out. It's x times 1 minus x squared dx. Well, for this, I guess we have to use substitution, u sub, and our u is 1 minus x squared. Well, okay, I guess we don't have to move the negative sign out. All right, so we want to bring this negative back in, and we need to have negative 2x. Well, so we do not have it yet, so it's better to have this 2 here and divided by 2. So then we have everything, right? So this is becoming 1/2 negative 1. So we got to be clear. X equals negative 1 and x equals 1. And over here, this times that is becoming du. And this is a square root to u, which is u to the power of 1/2 u. And here we want to specify this is x, right? Not u. Okay, so what do we have? The antiderivative of this is u to the power 1/2 plus 1, which is 3/2 divided by 1/2. 3/2, sorry. And then that's it. Well, we do not really have u, but we want to plug this u back, which is 1 minus x squared to the power 3/2 divided by 3/2. Well, we cannot forget there is a 1/2 factor here. And then x is equal to negative 1, x equals positive 1. So this is our definite integral. Well, what this is? I guess we don't have to simplify because we do note when we plug in x here and x equals 1 here and x equals positive 1 here, they're the same. There's 0 minus 0, which is 0. So on the left hand side, we have 0. Okay, that's interesting. For this particular left hand side, we got a 0. And what do we do? What do we do for the right hand side? Well, the right hand side, as we remember, it is supposed to be the line integral of this vector field, which is x and x times y. All right, and here, what we need to do is that we need to parameterize this part 1 and part 2 of the edge of this domain D. Okay, so this is the part 1. This is the part 2. This is the 1, negative 1. And for part 1, we have a couple ways to parameterize this. If you guys remember in our previous discussion, we could use either the x variable or the polar coordinates, right? So on top of it, we just use this polar coordinates. So when t equals 0, obviously, so t is between 0 and pi. When t equals 0, x equals cosine 0, which is 1, and y equals sine 0, which is 0, which is this point. And when t equals pi, x equals cosine pi, which is negative 1, and y equals sine pi, which is also 0, which is this point. Okay, so this is the t equals 0 and t equals pi. Okay, so how do we compute the line integral of this vector field on the part P1? Well, we'll explain a little bit later, but now obviously we are rewriting this as two parts of the line integral, which is on P1 we have x, xy. This is the vector field, and then plus P2, which is x, xy, the vector field, dot with this ds here. So on P1, obviously, what this vector field is becoming, this vector field has to be evaluated exactly on this path that is parameterized by cosine t and sine t. So what we should do is to just plug them in. So this is the cosine t and the cosine t times sine t. Okay, and also remember we do have this s to be represented by this. So what is ds? So remember ds is equal to the velocity vector or the tangent vector along the path times the dt. And for this P1 parameterization, what is the C? This is indeed cosine t, sine t. So C prime is negative sine t, cosine t. So we do have those two p's for evaluating. The first part of the line integral here, which is x y dot c prime t dt, and obviously we replace those two by their corresponding parameterization. So also on P1 we know the parameter is between 0 and pi, so we just set it. So this is the cosine t sine t dot this vector is negative sine t cosine t dt, right? Which is what? Let's compute cosine t times negative sine t plus cosine t sine t times cosine t dt. So this is what? This is from 0 to pi. I don't think we can simplify. So how about we just put those in two pieces? All right, so wait, maybe there's something wrong for my, oh, sorry. I did realize F1 is XY and F2 is Y. Did I write anything Yeah, so this is not the right vector field. So this is x, y, this is x. So now that is the right vector field. Sorry, F2 is y, not x. So we have to reverse those p's. So this is x, y, y, x, y, y. Sorry about this mistake. So with those, with this corrected vector field, we have a cosine t, sine t, y is sine t. So now we better to write them carefully. So this is x, y, y, x, y, y. So if that is x, y, we copy those here. This is not changed because this is the C2, and this is correct. This is the velocity vector along the path, and x times y is supposed to be cosine t sine t, and y is sine t. So now we have to compute it correctly here. Negative cosine t sine squared t plus sine t cosine t. Okay, so now everything should be consistent. We need to compute those two pieces. All right. So so now what? Now with this, well, there are two pieces. It's a little bit hard to compute, but still, we can set this first part by doing this u sub. The u is, we assume u is a sine t here. All right, so then du equals cosine t times dt. So this cosine t times sine t is times dt is du. So this is the u to the u squared du. So the antiderivative is u cubed over 3, and we have an extra negative sign. And then t is between 0 and pi for the first part. For the second part, this is indeed easier than you thought, I think. Similarly, you can treat the u to be cosine t, and then du equals negative sine t dt. So this is u du, negative u du here. So this is u squared over 2 is the antiderivative. So that is negative sign. Okay, so now we can see, we can compute those two. Well, but we realize they are all 0. It seems negative sine pi cubed over 3 minus negative 0, because sine 0 is 0, right? So this is a 0 minus 0. And for the second piece, this here, this is a cosine pi squared over 2 minus cosine 0 squared over 2. And this is becoming, well, because cosine pi is negative 1. Negative 1 squared is 1. And this is also just 0. So on part one, the half circle, we got the line integral of this vector field to be 0. And then we also need to have the part two. For the part two, we have this vector field. We need to evaluate this line integral. But on the part two, here, I want to use this to indicate. So how do we parameterize this red segment? It is indeed just the x variable itself, or t variable itself, for t between -1 to +1, right? So here, the p2 can be parameterized as x equals t for t between -1 to +1, and then y equals 0, I think. Is that right? Okay, so this is what we have. Okay, I think I have to pause a little bit.